Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We are discussing quantum systems, and in this chapter, let's quickly review what are the points that we have explored. So the first is that the quantum models that we have explored and also other quantum models, they offer new perspectives both from the point of view of applications as well as from point of view of understanding basic physics notions such as phases and phase transitions. Particularly, you will see the connection to classical problems. A single qubit, which is a zero-dimensional quantum system, by itself is not so interesting. Its partition function is just somewhat benign. But what is interesting is that you can show that the single qubit, as we did, is related to a one-dimensional classical Ising chain. We then went on to construct a quantum model in one dimension, and we were able to show that the partition function of the quantum model is related to the partition function of the two-dimensional classical Ising model on a square lattice. More generally, we were able to see that d-dimensional quantum systems in equilibrium are equal to d plus 1 dimensional classical systems, although with different coupling constants. We then went on to realize that if you take the quantum system to zero temperature, you will be working with the thermodynamic limit of the classical problem, and therefore by studying the zero temperature phase of the quantum system, you could say something about the classical phase transition of the classical system. You could also do the other way around. You could study the classical system in the thermodynamic limit and infer something about the quantum phase transition of the quantum system in one dimension lower. So with these ideas in mind, we decided to study the transverse field Ising model in its ground state, and we perform perturbation theory in the two limits of the transverse field Ising model, namely the ferromagnetic end and the paramagnetic end of the phase diagram. And we were able to see some very interesting results in the perturbation theory, that somehow the results on one end could be obtained by reversing the coupling constants from the results of the other end. And this led us to explore this further, and we realized that there is a quantum duality, that you can actually show that there is a dual model in which the coupling constants are indeed reversed, and you can show that there is a nice duality mapping. Okay, so this allowed us to conclude that we will not have a crossover as we change the transverse field as a ratio of the exchange coupling. We have eliminated by physical arguments that there will be a first order transition, and we believe now that there is going to be a continuous transition. So what we would like to do now is, we would like to discover this continuous transition more concretely rather than by just arguments, and this is what we are going to do in this lecture. We will build towards that, and in the next lecture we will actually solve the problem. Okay, so now I invite you to recall what were the nature of excitations in the paramagnetic side. So this is when the exchange coupling was much smaller than the transverse field. So transverse field is the strongest energy scale. There, if you kept the exchange coupling 0, then you would have the state where all the spins are x-polarized, and the kind of excitations that we had seen were created by the Ising interaction. And what Ising interaction would do on the ground state associated with the H is equal to 0, the fully x-polarized state, is that it will produce these two spin flips, x-flipped states. So these are states where the spins at these sites have become negative x-polarized. We then went on to understand that if I look at the sigma plus, sigma minus operators, they effectively produce hopping of these particles. So for example, if I take the state which we used to call Li, so here there is a negatively x-polarized state at x equal to 0, and there is one at x equal to the site I, you will see that if when this operator acts on this Li state, it will hop this particle to one site to the right. So that is, it will take this spin flip from I to I plus 1. So we can now imagine that this is some kind of particle that is hopping. So now the question is, can we really make these, can we take this very seriously and construct a theory where these objects are really particle-like, and you can write down a theory of these particles hopping and so on. So this is where we are headed. We want to make these X-flip excitations as truly quantum particles. Before we do that, we would like to see whether it is actually worth making this attempt. So it is very natural to think about a different kind of question. That is, we have an understanding of the paramagnetic state as a state where there are such dilute concentration of such X-flip excitations. What about viewing the ferromagnetic state using these particles? What will we see? Can we get some interesting description of the ferromagnetic state in terms of these X-flip particles? X-flip particles, remember, are the excitations in the paramagnetic state. So let's explore. So what I'm going to do is, I'm going to construct a device to count the number of these particles. So let's see how we'll do that. Can we count the number of X-flip excitations in any given state? Okay, so we of course need an operator for this. So if you think about this, you will realize that this operator, which I am calling nxi, counts the number of X-flip excitations at site I. How do you see this? Imagine that I sent the right polarized state, that is the state where it is polarized to the +1 eigenvalue of the X operator. You will see that this will give me 1, and 1 minus 1 will be 0, and so it will count no particles. On the other hand, if I am in the negative X polarized state, then xi will pick up an eigenvalue of -1, 1 and -1 will, 1 minus -1 will give me a 2, and 1/2 of that will give me 1, and it will count 1 particle. So this operator here will count the number of X-flip excitations at a site. Okay. Just as a simple check, you will see that the fully right polarized state has no X-flip excitations for any site. For any I, this is 0, which is exactly what it should be. Now I ask the question, what is the average number of X-flip excitations if I am in the ferromagnetic state? I am at the other end of the phase diagram. I am asking how many X-flip excitations are there in the ferromagnetic state. Okay. So please pause the video and try to find an answer to this before you continue. Well, I hope you found the correct answer. So the correct answer is 1/2. Why is that? If you look at any site, the up Z polarized state is a linear, equal weight linear combination of the plus X polarized and negative X polarized state. So that will count for you 0 and 1 particle with equal probability, X-flip particle with equal probability, and therefore you will get an answer of 1/2. Okay. So it looks like the state, the ferromagnetic state, has equal probability of being no X-flip or X-flip particle. Not surprising at some level. But here is something that you need to ask. What about the fluctuation in the number of X particles at a given site? You can ask this question legitimately because you know the operators and you can actually compute the fluctuation. Okay. And so what you have to do is you have to first define an operator to count the fluctuation. So please recall from your quantum mechanics that the fluctuation square operator is the operator square minus the expectation value of the operator square. Now this nx operator has a very nice property. If you square nx, you will get nx back. So you will see delta n whole square is just nx itself, because nx square will be nx, and that is the very simple and nice property of this operator. this just tells you that this number can be either 0 or 1. So, the solution of this equation as an eigenvalue, if you think of eigenvalues, solving eigenvalues, etc., you will see that this equation tells you the eigenvalue of nx is 0 or 1. That is exactly what this equation is saying. Okay. So, this is an important observation. So, nx square turns out to be nx. So, we are now in a position to compute the expectation value of the fluctuation. So, obviously, we should check the well known state, which is the right polarized state, and make sure that the fluctuation there is 0, and you can immediately see that it is 0 simply from direct calculation, that because it is an eigenstate of the x operator. So, there are no fluctuations, there are no excitations and no fluctuations in excitations if I am in the fully right polarized state in the limit of j equal to 0 and h greater than 0. Now, come to the other limit. So, when j is greater than 0 and h is equal to 0, the situation is completely different. So, we saw that the average value of x flip excitations at a site is 1/2, and therefore, the square of this is also 1/2 because nx square is equal to nx. Therefore, you immediately see that this root mean square fluctuation is 1/2. So, the allowed eigenvalues are 0 and 1, the mean is half, and the mean square fluctuation is half. So, in some sense, this is the maximum possible fluctuation that is allowed in this system. So, this means that there is a physical way of describing this, that the ferromagnetic state is actually a condensate of these x flip excitations. So, that is the statement that we are making here. So, what do we mean by condensate? So, this is a language that we borrow from Bose condensation. So, recall from your elementary statistical mechanics. So, if I have some bosons in 3 spatial dimensions continuum, and I cool the temperature down, and below some temperature you will see that the 0 momentum state will start getting finite occupancy. If you count the fluctuations in particles, you will see that that will also start to grow. So, this is exactly what we are seeing here. We are seeing that the average value is half and the fluctuation is maximum possible allowed in this system. So, this is a very physically insightful point we are making here, which is that we can view the ferromagnetic state as a condensate of the x particles. Okay, so now we are very much energized by this, because we understand that we can view both sides using these x particles. On one side x particles have condensed, on the other particles x particles have not condensed, they are just moving around a little bit. Okay, so this is the motivating point for looking further. Okay, so now that we see that we can extract some physical picture of different states using these x flips as particles, can we move forward and try to make them legitimate quantum excitations, of like quantum particle like excitations? Can we make them real quantum particles? So, let us see what we have seen so far. So, we certainly know that the x flips at different sites are indistinguishable, in the sense that I can't tell whether I made one x flip at site. If I have 2 x flips, I made one at site I and site j, I cannot tell which one is which and so on. So, they are indistinguishable. Most important thing that we found in the last transparency is that nx, the counting, the number of particles, the particles can be only 0 or 1. That means a site can hold only 1 particle or no particle. There is no question of 2 particles at a site. Okay. So, you have distinguishable particles in which each site can be occupied by none or 1 particle. What kind of quantum particles can satisfy these kind of properties? That is what we would like to explore. Indistinguishable quantum particles can satisfy these properties. Okay. All right. There are 2 possibilities. So, the first one are called hardcore bosons. This is different from what we call as canonical bosons. In canonical bosons, you can have any number of particles occupy the same site, for example. Hardcore bosons are different in that each side can take only one or no particles. There is no option of having two particles here. It's not allowed. Okay. The other possibility is you can have fermions. Why fermions? Because Pauli exclusion principle is applicable to fermions, which means that any state can be occupied by at most one particle. So fermions seems to be natural candidates for this, although hardcore bosons are equally good. Okay. Now, if you work through the algebra of this, of hardcore boson operators, you can show that the algebra of the sigma operators and the nx operators, etc., namely all the operators that we have used in the transverse field Ising model, they satisfy the hardcore boson algebra. So basically, this transverse field Ising model as defined itself can be viewed as if it's a hardcore boson problem. But you see, we are not able to make headway in trying to solving that using the hardcore boson framework. So this is why we want to see whether we can try to give these particles some fermionic interpretation. Hopefully, when we cast the problem in terms of fermions, we might be able to make more headway, and in fact, we might even be able to solve the problem. Okay. So the natural question to ask is, how can I change the problem of the transverse field Ising model to a problem of fermions? So let's quickly revise some ideas about fermions, which I'm sure in your physics training at some point you would have seen. So think of some kind of orbital, which is some kind of quantum state, like some single particle state, such as a 1s orbital of hydrogen atom or something like this, or it can be like an orbital at the sites of our where we placed qubits and sites of our one-dimensional lattice. So this orbital has two possible states. What is the state of the orbital? The orbital can be unoccupied. So we say that the orbital has no particle in it and denoted by a 0. So this is sometimes called the fermionic vacuum. You can also have the state of the orbital where a single fermion is actually occupying that state. There is a particle, quote unquote, sitting there. And this is the state which we denote by 1. That means the number of particles in that state is 1. Okay. So I have two states in this fermion Hilbert space, if you wish. There is a state where the orbital is unoccupied, and there is a state where the orbital is occupied. Okay. So I need some device to go from one to the other. So I'm going to define an operator called as a creation operator. It creates a particle which acts on the vacuum to give me the state 1, where there is single particle. So I create a particle in vacuum and it gives me the 1 state. Okay. And of course, I have to be able to, since I'm creating, I should be also able to destroy. And that's why I have an annihilation operator which is called C. It does the reverse. It takes the state where I have a single particle in this orbital. When you annihilate that particle, you get the vacuum state. Okay. Remember, the vacuum state is not the 0 of the Hilbert space. It's a different state. This state is actually a unit norm state. It's a non-zero vector in the Hilbert space. Okay, now comes the question, how do we impose Pauli exclusion principle? Pauli exclusion principle states that as an orbital, it's either empty or occupied by a single particle. That means if I try to create two particles, such state must go to the 0 of the Hilbert space, which means it's not an allowed state. So I have to ensure that the C dagger square must be 0. I have to enforce this as a condition. And same thing, C square must be 0, because if I take the singly occupied state and I cannot destroy 2 particles from the singly occupied state. So that should also be 0. So this will give us that C dagger acting on the state 1 will give 0 and C acting on the state 0 is 0. Right? 0 is these zeros on the right hand side here are the zeros of the Hilbert space, the 0 vector of the Hilbert space. Okay. Now, if you think about it for a moment, you will realize that if I take all of these things that we have discovered here, you will see that the C and C dagger operators satisfy a very important relationship called as the fermionic anti-commutation relation. What is that relation? That tells you that C dagger C plus C dagger must be the identity, or we can imagine that the state will get multiplied by the number 1. How do we see this? You just hit this left hand side on 0. So you will see that this thing, when it acts on 0, will give you 0 itself, and C dagger will take it to 1 and C will bring it back to 0. So the action of this on 0 will be as like multiplying by 1. You will get the state 0 back. And the same thing happens with the state 1, where this object will act and give you the same state back, whereas this object will kill this state. Okay. In addition, now we also have a very interesting operator we can define called as the number operator. The number operator little n is defined as C dagger C. What does it do? It takes any of these operators and multiplies it by the number of particles onto that state and gives it back to you. So if this acts on the vacuum state, it will get 0 times the state, which will give me the 0 state, and if it acts on the state 1, it will give me 1. And you can check that if I square this operator C dagger C and C dagger C, use this commutation relations, anti-commutation relations, and you will see that n square equal to n. Now this must ring a bell. We have seen some other operator, especially in the spin language or in the qubit language, which was satisfying this condition. So n square equal to n is another statement that the eigenvalues of n are either 0 or 1. Okay, so now I want to construct some matrix representations of these operators. So if I choose the basis to be 0 and 1, then I will see that this is C dagger and this is C, and n is this matrix. Okay. So if I give it the 0 state, it will give me the 1 state. If you give me the 1 state, it will give me the 0 state, etc. Okay. So this is the matrix representation of these operators. But you must have seen these things before. We'll come back to that in a minute. So what we now have is we have a space which we call W. It's called Fock space, especially when you have fermions. The Hilbert space has a special name after Vladimir Fock, who worked out a lot of these things, and it's called Fock space. And so this is the Fock space of fermions spanned by these. So this Fock space of fermions looks very much like our two-dimensional qubit space, and this is the connection we'll want to exploit. Okay, so we have seen how do we place fermions at one site or one orbital. Now what we would like to do is we would like to place fermions on a chain. So what we are going to do is we are going to place these fermionic orbitals at every site of the chain, and I am going to have periodic boundary conditions. Periodic boundary conditions, by that I mean that the site n is same as the site I. We will discuss the boundary conditions on operators, on fermionic operators in a minute. And so here at every place I have placed some fermionic orbital. Okay. Now at each site I can create one fermion and I can annihilate. If there is a fermion there, I can annihilate it. So I define operators C dagger I and Ci. Now what is the algebra of the operators that have to be satisfied if your fermions, your fermions defined, the fermionic orbitals are defined at different sites, and there are operators associated with each site, and what algebra do they satisfy? So you will realize that the algebra that they satisfy is written in this fashion. The anti-commutator of C dagger I and Cj is identity if the sites are same, it is 0 if they are different, and all the creation operators anti-commute with each other and all the annihilation operators anti-commute with each other. So this is the fermionic algebra. This is what tells us that we are talking about indistinguishable particles which are fermions, right? Identical particles which are fermions. Okay, so we would like to construct a base state for the full chain, basic state of the fermionic Fock space of the full chain. Now we are not talking about a single fermionic orbital, of the full chain. Okay, how do we create a set of base states for this? So you realize that vacuum, you start with vacuum which is denoted by omega, that is a state where none of the sites have any fermions. Okay, then I can have another state where there is one fermion in the full system, and that one fermion can be on any one of these sites. Okay. Next, I can have two fermions. If I have two fermions, I have to choose which two sites they are going to be in, and I have to create them in a certain fashion. Now the way we do this is, suppose I want to put NF fermions, I will choose NF sites out of these capital N sites here, and what I am going to do is I am going to order the sites in such a way that INF is the biggest of the i's, I1 is the smallest. So let's say I am doing for 3 particles, say I1 is this, I2 is this, and I3 is n minus 1, let's say. Then the convention I am going to choose is I will first create the smallest I particle, then the next one, and then the next one, and so on. Okay. So now you will see you can create many such different states with NF particles. How many states can you create? If you just think about it for a moment, it is N choose NF. That many distinct states can be created, and we have chosen a convention to create these particles because of the fermionic antisymmetry, etc. We will give you some different signs if you create them in different order, etc. Okay, so they form the basis of the sector of the Fock space where there are NF fermions. Now it is very easy for you to show that the dimension of this space is 2 to the n, and that just comes from the elementary combinatorics result that if you sum over all NF, N choose NF will give you 2 to the power n. Okay, I am just asking you to show this, but I just gave you the proof myself. Okay, so we have constructed a Hilbert space of fermions on the chain. Okay, now what I would like to do is I would like to prepare a little bit more background so that we can try to convert our TFIM problem into the fermion problem. So I imposed boundary conditions on the lattice sites. I said that the lattice sites at n is identified with the lattice site at 0. But when you are talking about fermionic operators, you can have many different types of boundary conditions. I will not get into the great details about this. I will just tell you that there are 2 types of boundary conditions that are fairly commonly used. The first one are called periodic boundary condition, is called periodic boundary conditions. It says that the creation operator at the nth site, which was identified as the 0th site, is same as the creation operator at the 0th. There is something called anti-periodic boundary conditions which we will need, that is why I am introducing this. The creation operator at the nth site, which is physically same as the 0th site, is taken to be negative of the creation operator at the 0th site. Okay, so this is called anti-periodic boundary condition. Okay, So now what I can do is, because I have fermions defined on a site and I want particle like excitations, right? I'm thinking I want to create some thought process where I have particle like objects. So you know particles have momentum. So I can try to write the site states labeled by sites to states labeled by momentum. So this is done by the technique of Fourier transformation, and I have simply defined the Fourier transformation here. So K is what is called as the crystal momentum, because you are in the one-dimensional lattice. So it's a one-dimensional crystal, it's momentum in the crystal. And in the way we have set up this problem, the crystal momentum lies in the interval minus pi to pi. Okay, this is where the crystal momentum lies. So what this tells me is that to create a particle with momentum k is equivalent to creating a particle at every site with a certain phase and linearly combining all such states. So that creates a particle with momentum k. Conversely, I can view anything defined, a creation on a site, as if it is a linear combination of particles with different momentum, right? And that is this state. Okay. Now, how do I impose anti-periodic boundary conditions? So there is a very natural way to do periodic boundary conditions. So what you do is you say that if you now decide, if you take this formula, what I am showing you here, and say that Cn must be equal to C0, so that will force that e to the ikn must be 1 for every k, okay, and that will give you that the allowed values of k in this interval from minus pi to pi are these quantities. If you choose instead the boundary conditions are anti-periodic, then e to the ikn, if I am choosing n even, this is important, you will see are given by these quantities, and that will ensure that e to the ikn when n is even is -1. That is this anti-periodic boundary condition. Okay, so we have now managed to define operators that create particles with a given momentum, and what the boundary conditions will enforce for you are the allowed values of those momentum k. I hope this is clear to you. Now, we have set up the platform to try to relate qubits to fermionic orbitals. Okay, so let's proceed with that exercise. So I start with the transverse field Ising model, and what I do first is I rewrite the transverse field Ising model in a more suggestive basis. So I do a basis transformation in the qubit space, and what I used to call as Z operators, in this new basis are called X operators, and what I used to call as X operators now are called Z operators. So if you think about this, you can see that this can be done by some pi by 2 rotation about the y of the qubits, y axis of the qubit space. Please work this out, it's actually pretty straightforward. Okay. Ultimately, you realize that this whole thing is just a unitary transformation on our old problem, so all the physics remains unchanged. So in this case, the ferromagnet will have all the spins polarized in the x direction, and the paramagnet will have all the spins polarized in the z direction. That's the only difference. And what we used to call as x flip particles will now become z flip particles in this language. Okay. So we write all operators in the basis of z operators on each qubit. So when we do that, now we see something very interesting. We see that this x operators looks like sigma plus plus sigma minus, where sigma plus is this and sigma minus is this. Okay, so suddenly you realize maybe this looks like C and this looks like C dagger. maybe we should try to connect up these guys, right? Maybe we should think of sigma as C and sigma minus as sigma plus as C and sigma minus as C dagger. But how will the states map? So given this realization that these things look like C and C dagger, we try to make this following map. We become a little brave and we try to make this map. We say that the up state at site I, right, remember that has no Z flip particles, that's this Z flip particles, that we consider as the vacuum of the fermion. And if I have the down state at I, then I have one Z flip particle there, therefore I think of it as having a fermion in that state. And with this, the identification that we saw is very natural. You will see that sigma plus I is Ci and sigma minus I is C dagger I. And Zi, mind you, is very nice operator now, is 1 minus 2 Ni. How does this work? So suppose Zi hits on the left here on the up state. So I'll get plus 1 as eigenvalue. So when this hits the 0 state, you will see it becomes 1 minus 2 times Ni acting on 0. Ni acting on 0 will give you 0, so it will be 1 times 0. So it will give you the correct eigenvalue of 1. What happens when Zi hits on the down state here? That will give me minus 1 times down state. And this will hit, when this object hits on this, Ni will pick up an eigenvalue of plus 1. So it will become 1 minus 2 times 1, which is minus 1 times the 1 state. So you see that the eigenvalues of this operator are same on either side of the dictionary, if you wish. And the Xi operator can now be immediately identified with Ci plus Ci dagger, because that's just this equation written in the C language. So you might think that this is fantastic because we have managed to convert the qubit problem into fermion problem. But there is an issue. This is not the correct mapping. What is the issue? The issue is that this condition of the fermionic anti-commutation relationship, if you wish, are not satisfied. Not only is this not satisfied, the other things are also not satisfied. So this is a problem. How do we deal with this? Okay, so this is a question that came up very early in the development of physics. So way back in the late 1920s, Jordan and Wigner actually worked out how to do this. So they realized that to create a fermion at site I, and to be able to satisfy all the commutation relationship, etc., I should check how many fermions I have already created. So if I am going to create a fermion at site I should check how many fermions are there to the left of the site I and multiply by a suitable sign so that the anti-commutation relationship has to be satisfied. How do we do that using qubits? The fermions will automatically do that because that is inbuilt in their algebra. But what about this? So what we have to do here, we have to enforce by hand that if I want to create at I, that is same as doing sigma minus at I, we agree with that. But when I do sigma minus at I should check how many downspin states are there to the left on any given state. Okay, so you can see that this is the string of operators to the left of the site I that will check the number of downspins, and basically you will get a phase meaning a number, a unimodular complex number, which is minus 1 to the power number of downspins to the left of the site I. Okay. Now remember, as qubits, as long as j is not same as I can move any operators around. So when I take dagger of this, I'll get this to be plus, and formally this will move to the right with the opposite order of multiplication, but since everything commute, I can just rewrite it in this fashion. So this is the identification for Ci. Okay. Now, what I have done is I have written the fermions in terms of qubits, but that's not what I really want. I want the other way around. I want qubits in terms of fermions. So what do? I note that this quantity 1 minus 2 Ni is e to the I pi Ni. This just follows from the fact that Ni square is n, the important relationship we had seen a few slides back. Okay. So now wherever I see Zi, remember our dictionary, Zi is 1 minus 2 Ni, I replace it by this quantity. Okay, and I must also tell you there is a very important relationship. Ni at any site will commute with Ni at any other site, because Ni at any site is made of two C operators on the same site and C dagger C, and on the other side is also made out of C dagger C, and therefore these will slide through freely because they are sliding through pairs of operators. And because of that, you can invert this relationship, and wherever you see Z, I can write this Ni and then invert that relationship, and you will see that sigma minus is this string times C dagger I. So another way to think about this, C dagger I knows how to create the string. It's there in the algebra. String meaning the number of, it will count the number of fermions occupied, etc., and it will create the sign correctly. What I am doing here is I am undoing the sign that it produces. That's what I'm doing here. Here what I did was, sigma i's don't care about the signs of the previously created spins, the down spins created on the sides left of the site I, and therefore I put the sign in to get the fermion. Here I am doing exactly the opposite. I have the fermion and I am removing from the fermion whatever it remembers about the number of the creation operator, whatever it does to handle the number of fermions to the left of the site I. So these are the beautiful relationships that we will be using to make the TFIM into a fermionic problem. Okay, so let me continue with trying to make TFIM into a fermionic model. So first thing you should do is, right now you should pause the video and you should check that these definitions that we gave in the last transparency will satisfy all the commutation relationship of fermions if you express them in terms of these spin operators. Namely, if you use this, you should see that the fermion commutation relationships are satisfied. If you use this, you should see that the hardcore boson or these qubit commutation relationships are satisfied. You should check that. Okay. So if you just work through a bit, you will realize that the key result that you need is just Zi, and there should be an I here and an I here. That is equal to 0. That's all the result that you need. Okay, and then you will see that everything is satisfied. Okay, how do we convert the transverse field problem into a fermion problem? So for this, you need a pen and paper. So please take it out and try to work this out yourself. Based on all the formulae that were there on the previous slide, we can now see that this product of xi plus 1 and xi will have ci plus c dagger I, and remember this will come with a set of the string of the z operators or the e to the I pi nj operators all the way to 0. And the same thing will come from here. But what you will see is that except for this term, all other terms will, there will be 2 times they will appear coming from the string associated with site I plus 1 and string associated with site I, and the only one that will survive, because these things square to 1, since zi square squares to 1, e to the I pi ni will also square to 1. So you will see that the only thing that is left is here, is this term, e to the I pi ni, and you see this object, e to the I pi ni times ci plus c dagger I, you can show as an operator is equal to Ci minus C dagger I. So what happens? This object will multiply through this, and you can see that that is exactly this. And so xi plus 1 xi, this whole thing is valid for 0 to n minus 2. That is, if you go back to our fermionic lattice, this one that we had defined, it's valid only up to here, n minus 2. If I take this one and multiply what happens here, something else will happen. So that's what we're going to see now. Okay, so if you look at what happens when I equal to n minus 1, that is the last site, I'm looking at the link which connects n minus 1 to n, which is like the link that connects the periodic boundary condition. You will now see that because the transverse field Ising model has periodic boundary conditions, xn will be x0 by definition, by construction. Therefore, this object will simply become C0, that is xn here. Just remember, I is n minus 1, so this is xn. That will just because C0 plus C dagger 0. But now you suddenly realize you don't have this full string of operators all the way starting from 0 to cancel this guy. So now what you do, you see that what is missing here is n minus 1. So you just add the n minus 1. And you will now see what you will end, and of course you have to keep another term to counter that, so that you will get e to the I n minus 1 nj minus j is equal to n minus 1 term, and you will get this term. Now if I work in a sector of the fermionic space where this operator is equal to 1, okay, this is called even parity of fermions, right? You see that sum over all nj is counting the number of fermions, and e to the I pi, this quantity will be plus 1 if the number of fermions is even, and minus 1 if the number of fermions is odd, and this is why we call this fermion parity. So if you work in that sector, you will see that the algebra will settle to this final expression, and note this all important minus sign that has popped up here. So you see, I can imagine this as Cn plus Cn without writing this, and now you will see that since it's coming out as C0 plus C0 with a minus sign, I now say that this is a problem with antiperiodic boundary conditions. Cn is turning out to be minus C0. So what we have managed to do is that this xi plus 1 xi term looks exactly in this fashion all the way up to n minus 2, and when I go to the n minus 1th site, which is the link connecting n minus 1 to the site n, which is same as site 0, you will get this term, and this is a problem with antiperiodic boundary conditions. And mind you, this zi's are same as these things here. Okay, so we have achieved something fairly non-trivial here. What we have managed to do is we have taken a qubit problem, which is a hardcore boson problem, and using this beautiful transformation invented by Jordan-Wigner, we were able to convert this to a fermionic problem. Okay? Okay, so let me summarize this lecture. So the main insights that drove us to look for some particle-like description of the transverse field Ising model was to imagine the x-flip states in the paramagnetic side and try to see that what is the ferromagnetic state in terms of that, and we realized it's a condensate. So we wanted to view the theory of transverse field Ising model as a theory of indistinguishable particles, and based on some algebraic properties, we found that you have to have an interesting non-local transformation between qubits and fermions, and this is called the Jordan-Wigner transformation. And using the Jordan-Wigner transformation, we were able to find a fermionic model associated with the transverse field Ising model. So before you view the next lecture, I encourage you to work out all the details of what we have done in this lecture, and make sure that you understand all the important conceptual ideas behind the transformation. And I'm sure you will be well prepared for the next lecture, where we will discuss the solution of the fermionic problem. We'll find the ground state as a function of the coupling constant. So I'm sure you will not miss the next lecture. I'll see you there. Bye.